Hello everyone, my name is Ikram Ben Said and I am an associate professor at the University of Mostaganem. Before I begin, I would like to thank the organizers of the second edition of the conference From Classical to Modern Analysis for their invitation and for giving me the opportunity to present my work here. So thank you very much. So our work, which is a joint work with Bouzien Berrajo and Fernando Leon Saavedra, lies in the field of operator theory on Hilbert spaces, and it is entitled Intertwining Relations, Products, and Absolute Values of Supraposinormal Operators. In this presentation, I will first recall some background on intertwining relations and explain their importance. Then I will discuss posinormal and supraposinormal operators. After that, I will present our new results related to products of supraposinormal operators. And finally, I will provide a new characterization of supraposinormal operators using absolute values. Let us begin with intertwining relations. Given two bounded linear operator A and B on a Hilbert space, we say that an operator T intertwines A and B if TA is equal to BT. This relation is generally denoted as follows. And at this step, it is important to point out that this relation is not symmetric and it is not transitive. And that if T intertwines A and B, then this does not mean that T intertwines B and A. So we should pay a particular attention to the order of A and B. Intertwining relations appear naturally in many areas, for example in spectral theory, quantum mechanics, and of course in operator theory. And probably it is very likely that you have already worked with intertwining relations without even realizing it. In fact, all the notions that follow can be considered as particular cases of intertwining relations. The first case, which is commutativity, is a trivial case because T intertwines A with itself. Similarity, for this case, let me recall that A and B are called similar if we can find an invertible operator T such that A is equal to T minus 1 BT. Since T is invertible, then if you multiply by T from this side, then this will go, and we will have simply that T intertwines A and B. Same goes for unitarily equivalent operators A and B. If U is unitary, then if you multiply by U in this side, then this will be the identity, and we will have UA is equal to BU, which means that U intertwines A and B. And finally, another special case is the notion of extended eigenvalues. So let me recall that lambda is called an extended eigenvalue of T if there exists a non-zero operator such that Tx is equal to lambda xt. But this actually means that T intertwines x and lambda x. So, why are intertwining relations important? First, it is clear that they transfer the action of A to B, and they actually preserve important spectral properties. For example, we know that similar operators share the same spectrum, for example. And secondly, they are also closely related to the invariant subspace problem. So, I recall here that if an operator T on a Banach space has a non-zero compact eigenoperator, I'm sorry I didn't mention, this is called an eigenoperator in this case, then in this case T has a non-trivial hyperinvariant subspace. So we can see here the importance of intertwining relations in the study of the invariant subspace problem. Besides all of this, intertwining relations also play a very important role in the famous Fugletti-Putnam theorem. And the Fugletti-Putnam theorem states that if an operator T intertwines two normal operators, then it actually intertwines also their adjoints, which means that if we have T n1 is equal to n2 T, then this actually implies that Tn1 star is equal to n1 n2 star T. So we have this implication that holds whenever n1 and n2 are normal operators. The Fugletti-Putnam theorem has many applications, and one of them is that if we consider the unilateral shift on L2, then thanks to the Fugletti-Putnam theorem, the equation xs is equal to s star x has actually no normal solution in L2. Now I'm going to present some concrete examples of intertwining relations. The following example considers a composition operator C phi, which is defined as follows in the space L2, and we are going to take a particular map phi, which is given by lambda x, and lambda is in 0, 1. This is to ensure that our operator is still bounded. Then Biswas, Lambert, and Petrovich actually proved that C phi intertwines the Volterra operator and lambda, the Volterra operator. And I recall that the expression of the Volterra operator is given by this integral. Another example is the weighted composition operator, which is defined by this expression. Then the weighted composition operator is bounded whenever H is bounded. And this operator actually intertwines the two Toeplitz operators T phi and T phi composed with omega. Now let us talk a little bit about posinormal operators. So everything started when Rayleigh observed that the Cesaro operator, which is represented by this matrix in L2, intertwines C star and C star D. In fact, it actually satisfies this equation. It's not an equation, it's equality, this identity. So in fact, this identity also happens to many other operators. For example, it also happens for the some unilateral weighted shifts and some parabolic, some composition operators which are induced by parabolic self-maps, and also the P-Cesaro matrix, which is given by this expression. So this actually motivated Rayleigh to introduce the concept of posinormal operators. So we're going to say that T is posinormal if T start is equal to T start PT for some positive operator P, and in other words, we are going to say that T is posinormal if T intertwines T start and T start P for some positive operator P. Some years after, mainly in 2013, Rayleigh again observed that the generalized Cesaro operator satisfies this identity where P and Q are positive matrices, So according to this, he observed again that there are many operators and that satisfy the identity T P T starts is equal to T starts P Q T. And this actually led to the concept of supraposinormality. So we're going to say that T is supraposinormal if we can find two positive operators P and Q where at least one of them has a dense range, and P T start is equal to T start QT. In this case, P and Q are called the interrupter pair of T, the couple. This theorem, which is actually a slight modification of the Douglas theorem, it actually gives many equivalent statements for posinormality. So all of these statements are equivalent. T is posinormal if and only if, for example, the range of T is included in the range of T stars, if there exists an operator, a bounded operator C such that T is equal to T star C, and all of these statements are actually equivalent. Although we have this, in fact, thanks to this theorem, we have the diagram, the following diagram, which shows the inclusion relations between the several classes of operators. For example, if T is normal, this means that T star is equal to T star T. Then if T is normal, then it satisfies this. And if it is hypernormal, then this means that T star is less or equal than T star T. And if T is hypernormal, then it is also a dominant operator. And in this case, I must first recall that if T is hypernormal, then all its translation for all lambda scalar T minus lambda E is also hypernormal. So thanks to this theorem, we can observe that the range of T minus lambda E stars is actually included in the range of T minus lambda E, and this means that T is also posinormal by taking lambda is equal to 0. And finally, it is clear that every posinormal operator is supraposinormal. We can simply take Q as the identity, and if you take Q as the identity, it is a positive operator, and we obtain, not Q but P. Otherwise it will be coposinormal, and it is a particular case of supraposinormality. And so we have all of these inclusions, and also invertible operators are posinormal because we can take, for example, C here. If T is invertible, then T star is also invertible, and so we can take C to be equal to T start minus 1 T simply. So we get that T is equal to T start minus 1 T, and this is the identity. So every invertible operator is posinormal. Now, what happened and what makes the posinormal class very special? It is special because it actually has a very bad properties. It's not like hypernormal operators. For example, we know that if T is hypernormal, then its translation are also hypernormal. But the posinormal operators are not invariant under similarity. Their translations are not posinormal, not necessarily. And if we consider the product of two polynormal operators, then the product is not necessarily polynormal, and we're going to refer to this question as the problem of the polynormal product. And furthermore, the powers of a single polynormal operator T are not necessarily polynormal. So it will be our purpose to investigate this problem in the next session. Basically, in this section, we will answer the following two questions. The first question is that does the Fugledeep theorem apply for supraposinormal operators? Is it valid? And then, under what conditions does the product of supraposinormal operators remain supraposinormal? For the first question, the answer is no. And we have provided a counterexample. In fact, if we consider the operator or the matrix T, then T is invertible, and so thanks to the Douglas theorem, it is also polynormal. And if we consider the two operators or the two matrices A and B, then it can be checked that T intertwines A and B, but TA star does not intertwine A star and B star. So unfortunately, the Fugledeep theorem does not apply, and it is a little bit intuitive because the class of supraposinormal operators is really large, and that's why it's not it does not apply for the Fugledeep theorem. Now, as for the second question, we investigate under which condition, under what conditions that the product of supraposinormal operators remains supraposinormal. This question was initially investigated by Kubrusli, Bourdon, Derek, and many other researchers. And Kubrusli and his co-authors in their paper, they actually proved if T and S are both polynormal and that T commutes with S star, then the product ST is polynormal. On the other hand, they also proved that if T is polynormal and S is normal, then the product ST is polynormal. In fact, we have actually proved that the polynormality of S is actually not required, and if we substitute this commutativity by an intertwining relation, then we can drop the polynormality assumption. So if we consider two operators S and T, and we assume that T is a supraposinormal operator, if T intertwines S star and lambda S, then the product ST is supraposinormal. I'm going to make the proof, to give the proof. So T is a supraposinormal operator with interrupter pay PQ, means that T start is equal to T start QT. And T intertwines S star with lambda S. It means that we have T S star is equal to lambda S T. Let us prove that ST is a supraposinormal operator. So we have ST P ST star is equal to ST P T start S start star, I'm sorry, not start, star. And since T is supraposinormal, then this means that we have S T start Q T S star. And now we have that T S star T intertwine S star with lambda S. So we have on the other hand we have this S T star is equal to lambda bar T star S star. So the first one is lambda bar T star S star Q, and this one is lambda ST. So if we can take both lambda and lambda bar, we will get lambda square, the absolute value or the modulus of lambda square. T star S star, I'm going to write it as ST star Q ST, and which is the same as ST star, the modulus of lambda square Q ST. So we have just proved that that the product ST is supraposinormal because this operator which is here, let's say Q tilde for example, is positive because Q is positive and the modulus of lambda is positive, and so we have just proved that ST is supraposinormal, and this actually generalizes the first theorem. As an example of our results, we have just proved that the operator which is defined by G beta is actually supraposinormal operator on L2, and this operator actually is just the product of R, C beta and the adjoint of the Volterra operator. C beta is this operator, which is the composition operator induced by the map beta x, and V is the Volterra operator, and R is this reflection or translation operator. Now, if we suppose that S and T are both posinormal and that T intertwines S star and AS, then we can prove that ST is actually posinormal. For the proof, T is posinormal means that T start is equal to T start PT, where P is a positive operator. And S is posinormal, it means that there exists a C such that S is equal to S star C. Okay? Here I'm going to write for some, I'm going to put it here, and I'm going to write for some positive operator P. Okay, and by assumption, T intertwines S star and AS star T. Okay, so I'm going just to make things more clear, clearer, I think we say this. I'm going to take the adjoint of this. It means that we have S T start is equal to T start S A start, and I'm going also to take the adjoint of this, so we will have also S start is equal to C start S. Okay, let us prove that ST is posinormal. So we have ST T stars S, T stars S star. I'm sorry, I don't know why I'm pronouncing start instead of star. I'm sorry. This is equal to T star P T S star. And S T star, which is here, is actually equal to this. And TS star is equal to this. So AS star T. And in addition, our operator S is equal to S star C. So T star S star C, A star P A, and S star is equal to this. So C star S T. Okay, but this actually means that we have ST star, and CA star is actually equal to AC star, yes, P AC star ST. So now let us observe that this operator, which is here, is positive, because I recall that if we have P a positive operator, then T S T star, for example, T star is also, oh, I'm sorry, T P, the multiplication of T star is also positive. The same goes with this. So this operator, which is here, is positive, and we can write is equal to S T star. I can write this as, for example, P tilde ST. And so we have just proved that ST is posinormal with interrupter pair, with interrupter and we have just finished the proof as wanted. Now finally I'm going to talk about the absolute value of supraposinormal operators. So let me recall that the absolute value of an operator is the unique positive square root of T star T, which is by definition given by this expression. Now we know that T is positive if and only if the modulus or the absolute value of T is equal to T, and T is normal if and only if the modulus or the absolute value of T is equal to the absolute value of T star. Is it possible to have a similar result for a supraposinormal setting? Well, the answer is yes, and this is what we have just proved. So I'm going to start. If T is a supraposinormal operator, it means that T P T star is equal to T star QT. And by definition, we have that this is equal to the square root of P T star. Okay. Now this is exactly equal to T stars, the square root of P. Of course, we will take the adjoint, but the square root of a positive operator, the square root of any operator actually is always self-adjoint. So we have this is equal to this. And so it is not necessary to write, sorry. But this is equal to P, so it is equal to the T stars PT, and which is equal by definition to T stars QT. And we're going to do just the same process, t starts the square root of q, but since the square root is self-adjoint, then we can take the self-adjointness here, and this is exactly equal to the square root of q t star, and this is by definition is equal to the absolute value of q, the square root of q t. Okay, and this finishes the proof. As a consequence, t is polynormal if and only if the square root of q p is equal to the identity, so we will have that this, and we can also have this corollary, which uses the polar decomposition of an operator. And the weighted mixed Schwarz inequality for polynomial operators is given by this. Finally, I'm going to finish this presentation by proving that unlike the quasi-normal operators, this identity does not hold for supraposinormal operators. And for this, we just consider this polynormal square matrix, and we can prove that the modulus or the square root of t squared is different from the square root, the absolute value of t squared. Okay, I hope that you enjoyed the talk, and these are the references, and thank you very much for your attention. If you have any questions, please just write me. Thank you.